All right, good afternoon or good morning, everyone, just depending on where you're at in the country. Just wanted to take a second to introduce myself. Some of you may know me. I think there's several of you out there that may not. My name is Brit Davis. I'm one of the automation and safety sales managers for IDEC. So today what we're going to be going over is scaling and data conversion in the FC6A series PLCs. I'm going to do a short presentation and then we'll jump into some programming examples. After the webinar is over, and it'll probably be sometime later this week is my guess, I'm not 100% certain, is that you guys will be getting a copy of the presentation. You'll get a copy of the program that we develop together, and I will document it. So there's run comments and things like that you guys will be able to follow along in the program a little easier than if it was just straight ladder logic. Also, for sitting through a webinar and listening to me babble for a little bit, everybody also gets a free copy of Automation Organizer. And after the webinar is over, our Marcom department will send each of you an email with instructions on how you can go about getting that software and how to convert the demo software to the full version, all that kind of stuff. The Automation Organizer software, it's a suite that houses really every piece of software that you're going to need for IDEC PLCs and IDEC touchscreens. It has WinLadder, which is what we're going to be using today. It also has Window INV that programs all of our touchscreens. So with that, we'll go ahead and jump in. As we go through this, at the end of the webinar, I will try to answer any and all questions that you guys may have as we go through this. Feel free to, to post that in the questions section. Your dashboard may look a little differently than mine does. But again, feel free to type in any questions you guys have as we go through this, and we'll do our best to answer them at the end. Also, what I will do too is after the webinar is over, I'll go through and put a document together of all the questions that were asked, put those in a PDF. That way you guys have those as well, the questions along with the answers. So, if you're time limited or you just don't want to stick around or what have you, then you'll still have the information. All right. So the first thing that we want to look at before we start converting data or scaling data, we need to kind of have an understanding of the different data types that we offer in the PLC. So when you're talking about items that can have a value, something that's not a bit where it's just on or off, we've got 5 different data types, and you can see them there in the chart below. We've got a word and an integer. Both of those are 16 bits, or they take up 1 data register. Okay, a word is a positive whole number, anywhere from 0 to 65,535. An integer you can think of really like a word, it's just split across the 0 point. So an integer has the first bit as the sign bit, whether it's positive or negative. That can have values from minus 32,768 to plus 32,767. Okay. The other 3 there, a double word, a long, and a float, those are all 32 bits, and those take up 2 consecutive data registers. And you guys will see this as we start doing the example. Okay, so a double word is nothing more than 2 words back to back, 32 bits, and that can hold values from 0 to 4.294 billion. A long is similar to an integer, right? It's split across the 0, it's 2 words, so you can have values from minus 2.14 billion to plus 2.14 billion. Floating point, 32 bits, 2 consecutive words, minus 3.4 times 10 to the 38th to 3.4 times 10 to the 38th. And those are the 5 different data types that, that we can work with in the PLC. Okay. Now, if we want to convert from one data type to another, the instruction that we use is the CVDT instruction, which stands for Convert Data Type. In that first graphic there, you can see where we've got a normally open contact up here, and then we've got a convert data type instruction. So the convert data type instruction does need an input to tell it when to execute. We have a source, S1, Basically, that is, what is it that we want to convert? And we have a destination, D1. Where do we want to store the converted value? For example, down below, we have a normally open contact of input I0 with a one-shot here. This is a single output up, SOTU. And what that means is we're just looking for when I0 turns on to execute whatever is after this. Okay, we don't care how long I0 is on, how long it's off. All we're looking for based on this SOTU, this single output up, is the transition when I0 goes from off to on. When that happens, we're going to convert a data type from a float to a word, F to W. We're converting a source, whatever is in data register 0 and data register 1, because this is a float. So remember, we're looking at 32 bits, 2 consecutive words. So D0 and D1. We're converting that into a word, storing that in destination D1, in data register D2. So over here to the right, you can see our source as a float. We've got an example value here of 3.141593. When we do the conversion and we convert that to a word, it basically just takes and puts the chops off the decimal point. Right? It converts that to a 3, which is what we're seeing down here. When input I0 turned on, we've got 3.141593 in D0 and D1. That gets converted to a word and stored in data register D2 as a value of 3. Now we can convert from one data type to another. We can also scale data. One of the examples that we're going to do later is, let's say you've got a pressure sensor, a 0 to 10 volt pressure sensor coming into your PLC. And you may want to scale that maybe between 0 and 100% or between whatever values. But there's a couple of ways that you can go about scaling that. One is to use this scale instruction. Okay. What the scale instruction lets you do is you can specify a minimum and a maximum for both the input value that's coming into the instruction and also the output value. Okay. The value that's coming into the instruction will be scaled linearly between your output minimum and your output maximum settings. You define those. Whatever range you want that to be is fine. The scale instruction also has a deadband setting. Now, what that lets you do is, in essence, lets you kind of filter the input that's coming into the instruction. So if you have an input that's kind of bouncing around a little bit and you don't necessarily want small changes to affect your output, you can use a deadband setting. And we'll go over an example of a scale instruction without deadband and also an example with, so you can kind of see the difference. Okay. Some of the parameters of that scale instruction, you'll see we've got 3 sources that we need to enter. That's what the S stands for in any of our instructions. S is for source, D is for destination. Our first source here is our input value. And in our example, it's going to be that 0 to 10 volt pressure sensor that's coming into the PLC. Source S2 is a collection of data registers. What I mean by that is we're going to specify just one data register for S2 as the starting address. Everything else will fall out from that. As you can see here, it's actually going to use 5 registers. So for example, for S2, if we use, for example, data register D10, we're actually going to be using D10 for the input max value, D11 for the input minimum value, D12 for the output maximum value, D13 for the output min value, and D14 for the deadband value. Okay, so we're actually using 5 consecutive registers there. Our source 3, S3, is a bit. And all this is an initialization input. So as you guys will see, once we do the example of the scale instruction, there's some areas within the dialog box for that instruction where we can set up all these values. What the initialization input does is whenever that gets turned on, it will move whatever values we configure in the instruction into those data registers, okay? So what that means is when you're in the field, in the program on the fly, you can adjust the values in these data registers to whatever you want them to be, okay? If you want them to go back to their default values that you hard-coded into the instruction, you just turn on the initialization input. That'll move the default values back into those registers for you. We've also got S4 here. It's also a collection of data registers. This is using 6 registers, okay? Our output value here is going to be in S4 plus 0 and plus 1. This is a floating point value. 32-bit value takes up 2 consecutive data registers, okay? So this is going to give us a scaled output value in floating point. We've also got S4 plus 2 and plus 3, again, a 32-bit floating point value. It's going to show us our output value for our deadband. And this will make more sense when we do the application. S4 plus 4 is the absolute value difference between the output value, your S4 plus 0, and the output value deadband, the S4 plus 2. S5 is a couple of internal relays. Okay, and just like when we define data registers, whatever we put in here for S5, for example, if we use internal relay M50, we're also going to be using M51 here for the input value warning. Okay, so S5 plus 0 is just an indication that the output value has changed. This is going to be on only for one scan, and it turns on whenever the difference between your output value, S4 plus 0, and the output value deadband, S4 plus 2, is greater than whatever you have set for your deadband setting, okay? Since this is only on for one scan, if you're going to use this in the logic, what I would recommend doing is you could have a normally open contact of whatever this address is with a single output up, and then going to a set instruction to set another internal relay so you can catch it, okay? The scan, and for those of you who may be new to PLCs, or if you just don't know what the scan is, what the scan of the PLC is a 4-step process, and this is common among pretty much all PLCs on the market. Basically, what the scan entails is a process that reads all of your inputs, executes your logic, updates your outputs, and then does housekeeping and communications at the end. Okay, so it's a 4-step process. How fast that happens is called the scan time. And you'll see scan times of PLCs, depending upon your program, how big it is, what's turning on and off on each scan. You'll see scan times in the neighborhood of 5 milliseconds, 10 milliseconds, 20 milliseconds, in that kind of a range. All right, S5 plus 1, that bit is an input value warning. That will turn on whenever your input value to your scale instruction is either greater than the input maximum value that you've defined or less than the input minimum value setting that you've defined. Again, you get to specify an input maximum and minimum range. So if the input that's actually coming into the instruction is outside of that range that you specify, that's when this S5 plus 1 will turn on. Okay, that's the scale instruction. And again, we're going to do some examples of this. Okay, another way that you can scale data is by using the XYFS, which stands for XY format set instruction, in conjunction with either the CVXTY, which is convert X values into Y values, or the CVYTX instruction, which is the convert Y values into X. Okay, so XYFS can be used with either of those two convert instructions. Okay, now the XY format set, you guys can see the structure of the instruction here. We've got to have some sort of an input to turn on the XY format set. Okay, what this lets you do is you can define up to 32 sets of points, 32 sets of XY points that you can scale your value between. Okay, where this is really handy is if you've got something that is nonlinear, right? The scale instruction is great because it gives us a range that we can set. It gives us floating point for precision, but it's only linear. It's between 2 points, 2 sets of points. So if you've got something that's nonlinear, you can use XY format set and a convert X to Y instruction, or convert Y to X. Okay. So those two convert instructions, again, what they do is either convert X values into Y or convert Y values into X, just depending on which way you want to go with the conversion. Okay. All right, so some additional information here. You can have up to 30 different XY format set instructions in a single program. Okay, so I could have different scaling factors for different things, right? Up to 30 different sets of up to 32 points apiece. Now, when you're using XY format set and the convert instructions, what ties those two instructions together, what tells the convert instruction which XY format instruction to look at to actually do the conversion, is determined by our source one, our S1 value in each of those instructions. When they're the same, that's what ties them together. And you'll see this when we do the example. Okay. So what I'm going to do now is I'll jump into Wind Ladder and we'll go over some examples here. And let me just make sure, yeah. Okay, Wind Ladder looks like it's up. So whenever you open Wind Ladder, the first thing that you're going to want to do is just select the PLC that you're going to be working with. Now, here in my home office, I've got an FC6A D16, which is already selected. If I didn't have that already, what you would do is just go up to Configuration, click on PLC type, and that will open up a list of the PLCs that we've manufactured for just about the last 30 years or so now. And you can see we've got FC6A D16 here, and that's the one I want to use. To set everything up, to configure it, I can click on this Module Configuration tab. One of the changes that we made with the FC6A series was this graphical configuration tool, which makes it a lot easier. You can simply do a couple of things. Either go over here and grab whatever digital I/O, analog I/O, cards you have, PID modules, HMI modules, what have you. Grab all this stuff just from a list and drop it in. The other thing you can do is you can click on this Read Module Configuration button. Now, what this is going to do is, since I'm connected to the PLC, right now I'm connected over USB, which we can see this down at the bottom left of the software. Right beside where it shows the model that we're using, it'll show how we're connected. And right now I've got a USB cable plugged in. So if I click on this Read Module Configuration button, what it's going to do is go out to the PLC and read all of the cartridges and cards that are connected to it. Okay, so if I click this, it's going to come up with a warning and tell me existing modules are going to be replaced and the settings will be lost. In other words, if you already have a bunch of cards and things configured here, things configured in the PLC, and you do this, it's going to overwrite what you've got here already. In my case, that's fine. I've just got this PLC with no cards. I want to do this, so I'll click yes. Okay, so once it does that, it goes out and reads what I've got connected. And what I have is a couple of cartridges here on the left side of the FC6A Plus. I've also got an analog I/O, or not I/O, just analog input card connected as well. This top cartridge is one that we're going to be using. This is an analog I/O cartridge that will read temperature. So what I've got here is some thermocouple wire with the ends twisted together to simulate a thermocouple plugged into that cartridge. I've also got on the analog I/O card, I've got a 0 to 10 volt simulator plugged in so I can vary the voltage going into that analog input card from 0 to 10 volts to simulate that pressure sensor. Right. Now on the analog cartridge, if I want to configure that, I can just click on it and click the configure button. Okay. Now I've physically got the thermocouple wire going into input 0 here, this top one. Type K is fine, it's thermocouple wire. Data type I can change between binary data, which you can see it shows a min and max value here of 0 to 4095. The reason it's showing this is because that cartridge is a 12-bit cartridge. And in 12 bits, this is the range of the values that you can get. Well, this is temperature. I really don't want to show this from 0 to 4095. So what I can do is change from binary data. If I click in here anywhere, I'll get a drop down. I can change that to either optional range, Celsius, or Fahrenheit. So if I pick Fahrenheit, what this is going to show is a minimum value of minus 328.0 and a maximum of 2,372.0, okay, which is just the standard default range for a type K thermocouple. This data is going to get stored in data register D8170. It's one of our special data registers, okay. Now, one thing to point out here, and I'm sure you guys have already caught it, is, okay, we've got values of minus 328.0 and plus 2372.0. Those are floating point values. I just said those take 32 bits and get stored in 2 registers. How are we wedging that data into one register? What we're doing is we're playing a little game in the firmware. What we do is we read the temperature here, we multiply it by 10 to get rid of that 1 decimal point of precision. So we actually have minus 3,280 to plus 23,720. That's an integer. That can fit in one data register, 16 bits. So that is what's getting stored in D8170. So when we use this in the logic, what we need to do is we'll convert this D8170 from an integer to a floating point value. We'll divide that by 10 to get that 1 decimal point of precision back. And then we'll be able to see the floating point value of the temperature. All right, and again, that data is going to be in D8170. That's what we're going to work with in our convert data type instruction. The next thing I want to set up is the analog input card. So I'll click on the analog card, come down here and click on the configure button. To set up the analog card, I need to specify the data register, the starting data register that I'm going to use. This is very similar to the S2 setting in that scale instruction, where I said we'll specify the starting register, but we're going to use 5. This is very similar. For example, here, if I configure the analog card to start at data register 1000, you can see here right beside the ellipsis button, it's going to use D1000 through D1007. So it's actually using 8 data registers, okay? Now, what I've physically got connected here, that 0 to 10 volts simulator, is physically wired into analog input 1 on my card. So I can leave analog input 0, 2, and 3 as unused. I don't have anything connected to them. I'll set up analog input 1 here as 0 to 10 volt DC. And as you guys can see, this card, the FC6A J4CN1, we can do voltage, current, temperature, whether it's thermocouple or RTD, okay? In my case, again, I've just got a 0 to 10 volt DC input coming in. I'm gonna leave it at binary data, that's fine. We'll do the scaling outside of this instruction. The minimum is 0, the max is 65,535. If you guys remember from the presentation, that's just the max value range that you can have in a word, 16 bits. This card has 16-bit resolution. So again, we'll have values from 0 to 65,535, and they'll be stored in data register D1002. If I click OK, that's really all I need to do as far as the configuration. It's set up so I can go and start programming. So I'll click here on main program to get back into our workspace. The first thing I'll do is I'll do a convert data type instruction to convert the temperature data that's coming in from an integer to a float. And then I'll also do a division instruction to convert that into the real temperature. Remember, we need to divide it by 10 to get the real temperature. So let's do that. Maybe I want to do this once a second, for example, and you can decide how often you do it in your program. I'm just doing this as an example, so I'll go out and grab the temperature once a second. For a real application, maybe you want to do it every 5 seconds, 10 seconds, 30 seconds, a minute. Just depends on the application. So let me go get a normally open contact. And if I go to my Home tab in the instructions section here of the ribbon, if I click on Basic, the very first instruction there is a normally open contact. I'll left click to drop that in, double click to edit it. And I'm going to use Special Internal Relay M8121. Now what that is, it's a 1 second clock bit. Basically it's on for half a second, off for half a second, on for half a second, off for half a second, continually. You don't have to do anything to make it do that, it just does it. It's something we've already got pre-programmed in the firmware. Okay. Now, if I want this to happen just once a second, what I can do is I can use a one-shot, a single output, and those are under basic instructions. About halfway down, I've got single output. I can choose from single output up or single output down. Okay, they're basically the same thing. The only difference is single output up is looking for whatever comes before it to turn on. Single output down is looking for whatever comes before it to turn off. Okay, I can choose either one will work fine. I'll pick single output up. So whenever it sees M8121 turn on, as soon as it sees it turn on, it doesn't matter how long it's on, if it's on, when it went off, just that transition from off to on, that's when it's going to execute whatever code we put out here. So let me go grab a convert data type instruction. That's going to be under your advanced instructions, underneath data conversion, and down to CVDT or convert data type. Okay. Now, you'll also notice all of our instructions have either a 1, 2, 3, or 4 character prefix to them. For example, convert data type is CVDT. Alternate output is ALT, and alternate output is what you would use if you want like one push button to be able to do a start and stop function. You push it once, it turns the bit on, push it again, it turns it off. So what I'm getting at is if you don't want to have to go through these menus, or you don't want to have to add things to your icon bar or go through the toolbox to get the instructions, if you know what they start with, you can simply go in the workspace and start typing it, what it starts with, and you'll get a list that pops up that you can choose from. Just another way to get code into your workspace. So if I do a CVDT, again, I want to convert from an integer, and I want to convert to a floating point. Okay. Again, we're converting from an integer because that is how the temperature is stored in the PLC that's coming in from that cartridge. So my source 1 here is going to be data register D8170. Okay. Our destination D1, our first destination and our only destination, is the data register where we want to store the floating point of the converted data. And I'll just pick a data register in the PLC, for example, D0. So this is going to be the raw temperature in float. Okay. So again, this is going to use D0 and D1, 32 bits, as a floating point value. Okay. So great. I've got the data converted from integer to float. Now I just need to do a division by 10 to remove that multiplication by 10 that we do in the firmware. So what I can do is put a ladder line down and put in a division instruction. And the division instructions are underneath advanced, binary arithmetic, and div division. I'll left click to drop that in, double click to edit it. Now, one thing we want to be careful of here, since I'm going to divide D0, D0 is now a floating point value. I want to make sure in my division instruction here that I change this data type from a word to a float. Okay. If I don't do that, if I would have just left this at the default, which is a word, it would only, when I do my division, I'm going to use source 1 of D0. If I leave this as a word, it's only going to use 16 bits, just D0. If I want to get all 32 bits, since it's a float, I have to change it to float. Now it'll use D0 and D1 as 32 bits. Okay. If I would have just left that at D0 as a word, our calculation and our temperature would have looked really weird. All right. So what I want to do again is divide D0 and D1 as a float by 10, and I can store that in destination D1. Our first destination is where do I want to store it? It doesn't matter. I can pick any data register that I'm not using in the PLC. For example, maybe I use D2, data register D2. And this would be our real temperature and float. Okay. All right. Let me go ahead and download this, and we will take a look and see if it's working. All right. Okay, so it downloaded. One of the things you're seeing here is something I must have left on in my in my software. One of the things that you can do is actually look at the mnemonic code, the actual code and the number of steps that each instruction is taking in the program. For those of you guys who happen to be around my age and had to use handheld loaders before we had software, you'll recognize this stuff. It may make you shiver a little bit too, but you can still view that if you want. Just in your view tab in this show hide section, there's this mnemonics checkbox. You can turn that on or off if you want to see that. All right, so what I'm going to do now, I downloaded the program. I'm going to go online and go into monitor mode. So I'm looking live at the PLC. Okay. So what's happening here is M8121 is turning on for half a second, off for half a second. When we see it turn on, we're converting the temperature in D8170. And with my little hillbilly thermocouple wire that I've got twisted together, it thinks it's around 77 degrees, which is probably about right. It converts it into a floating point value, stores it in D0 and D1. Then we come down here to the division instruction. It divides D0 by 10 and stores it in D2. And again, D0 is a float, so it uses D0 and D1. So we can see that the temperature here in my office is about 77 degrees. Good enough. That seems to work okay. So let me go back out of monitor mode and let me delete this little ladder line here. We don't need that. Just put an extra one in. Let me hit enter to make a new rung, and we'll take a look at the scale instruction. Now, if you guys remember from the presentation, source 3, S3 of that scale instruction was the initialization bit. And again, that's what is going to copy the values that we put in the scale instruction into the working registers. There's a number of ways that you can go about turning that bit on. You can do it on demand whenever you want to. Just for example's sake, the way I'm going to do it here is I'm going to use another special internal relay that we have called M8120. So I'll get a normally open contact and I'll address that to M8120. Again, that's another special internal relay. It has a predefined function. It's called the initialize pulse. I call it the first scan bit. The reason I call it that is because this bit will turn on for the first scan of your PLC whenever you power cycle the PLC or whenever you download a program. So this bit will turn on just for one scan and then it turns off. So we call it an initialize pulse because it's great for initializing things. So what I'm going to do is have this turn on an internal relay just for one scan, and whatever internal relay here that I use, I'll grab an output here. Whatever internal relay that I use here is going to be the initialization bit for our scale instruction. And I can use any internal relay I want that I'm not using. I'll just use M0, and that's going to be used to initialize our scale instruction. Okay. So on the first scan of the PLC, it'll turn that bit on, and then after the first scan, this bit goes off. Okay, that's how that works. So what I'll do now is I'll put in the scale instruction. And if you guys remember from the presentation, that also needs an input to tell it when to scale. So just for this example, I'm going to go ahead and use what we did up here in rung 1. I'll use M8121 with a 1 shot up, just so it does it every second. Again, you can do it in your applications whenever you want, whatever makes sense. You don't have to do it once a second. But just for example's sake, that's what I'll do. So I'll get a normally open contact of M8121. I'll put in a single output up, again, just so it happens every second. And now I'll put in the scale instruction. So like we looked at in the presentation, I've got 3 sources and 2 destinations here to enter. Again, source 1 is my input value. So if we're going to scale that analog input, that 0 to 10 volt analog input, that was coming into D1002. This comes from our analog card configuration, right? We told it we wanted it to start at D1000, and for analog input 1, which is where I physically got the 0 to 10 volt signal coming in, that was using D1002 to store the value. So this is our 0 to 10 volt analog input. Source 2, that was those series of 5 control registers, 5 data registers consecutively. So whatever data register I put in here, for example, if I use D10, we're actually going to use D10, D11. It's actually going to use more than 5 registers because we've got D12 as a float. So it's going to use D12 and D13 as a float for our output maximum value. It'll use D14 and D15 as our output minimum value, again, a floating point. And it's going to also use D16 and D17 as the deadband. You guys will see this in just a second. Okay. So know that this is actually allocating D10 through D17 for this instruction. Okay. I can see that if I click this device allocation button here. Since I used D10 as the starting address for S2, it'll show you I'm using D10 through D17. Okay. You'll see it breaks it up here as far as like D12 and D13, output maximum value. One is the high word, one is the low word. We're going to look at it as 32 bits as a floating point. Same thing for the output minimum value. We're going to look at these 2 registers as a float. Same thing for deadband. Okay. All right. So for S3, source 3, that's my initialization input. Again, that's going to be internal relay M0 that we just used. Okay. So on the first scan of my PLC, I'm going to initialize this instruction. What that's going to do is it'll copy all the values that we enter into the settings tab into the working registers. All right, D1, destination 1, is an output register. I'll specify D20 as the starting register for this. Now, if you remember from the presentation, we talked about the output value of the scale instruction was in floating point. So what this is going to do is give me D20 and D21 as a float is the output value of this instruction. It's also going to use D22 and D23 as the output value for our deadband. And you guys will see how this works when we go through this. That's also a float. It will also use D24 and D25 to show the amount of output change between D20 and D22, those 2 floating point values. Okay, so we are actually using D20 through D25 with D1 here. Okay, D2, destination D2, that was a couple of internal relays. You remember M20 was the output value change notification that turned on only for 1 scan. And we also had M21, which is going to be the input value warning. Okay, so we're specifying a couple of internal relays here. So far, so good. Now, one other thing that we've got to do, though, is configure this settings tab. Okay, my data type here is a word, which is fine because that's what I've got coming into this. I've got 0 to 65,535 representing 0 to 10 volts from my analog sensor coming in. So for my input value, my maximum value, 100 is fine. I don't really need to change that. Actually, I do need to change this. I want this to be the full range of the analog card. So my maximum input maximum value will be the maximum allowable, 65,535. Okay. My input minimum will be 0. So when I have 0 volts, I get a value of 0. When I have 10 volts, I'll get a value of 65,535. What I want to scale that to is what I enter here, the maximum and the minimum for my output. So the way this is set up right here by default is it will scale 0 to 65,535 into 0 to 100 as a floating point value, so I can see it as a percentage. The deadband, to start with, we'll leave this off at 0. You can see over here it says 0 is disabled. So we'll leave it off to start with. We'll see how this works. Then I'll come back and I'll put in a deadband setting so you can see how that works as well. Okay. So these are the values I want for my default values. And again, whenever I turn on M0, those default values will get pushed into these working registers. Okay. All right, let's go ahead and download that. And I'll go into monitor mode. And we can see here, D1002 right now has a value that's bouncing back and forth a little bit, but it's about 27,960. And again, what I've got is a 0 to 10 volt simulator that's just operated off of a potentiometer. So as I increase that value, you'll see, or as I turn the potentiometer rather, you'll see D1002 increasing. You'll also see D20 over here, destination 1, D20. You'll also see that increasing. So for example, if I max this thing out all the way to the right, I should have a D1002 value of 65,535. That's 10 volts. I'll also see a 100.0 here in D20. Again, we scaled this from 0 to 100%. So if I do the opposite, if I take this all the way back to the left and send it 0 volts, and again, you can see, the potentiometer's bouncing around a little bit, 0, 1, or 2 here, but that's just about not enough to affect the output. It's still showing basically 0 volts here. So again, this is scaling it linearly between 0 volts and 10 volts, gets scaled into a percentage and floating point between 0 and 100. Okay, so let me do this. Let me also go ahead and I'm going to make a custom monitor dialog box. So if I go to custom and new custom monitor, what I can do in here is I can enter whatever devices that I am interested in looking at. For example, if I want to look at the raw analog value from 0 to 65,535, I can look at D1002. Okay. If I want to take a look at the output here and floating point of the instruction, I can look at D20. Okay. And again, I want to change this monitor type to a float because I'm looking at it as a float, 2 consecutive data registers. Okay. So I can see that. That's good. Now I'm also going to go ahead and put in here data register D22. Okay. And that is the output value for the deadband. Okay. And right now, since we're not using any deadband setting, if you remember in the dialog box, we set it to be 0 for off. So what that means is as the output changes, that value will be copied into our deadband output here as well. In other words, D20 and D22 will be the same if you're not using any deadband. Okay. No matter what I adjust the 0 to 10 volt input to, D20 and D22 will have the same value if I'm not using deadband. Okay. Now I'm going to go ahead and save this custom monitor dialog box. I'll save this as, I'll call it scaling. Okay. This gets saved as part of your project, and whenever you go to download, you can choose whether or not you want to include those custom monitor boxes on the PLC or not. So you can keep them just on your laptop, or you can download them as part of the program. All right, now let me go ahead and change the scale function just a little bit. Let me put some deadband in. For example, let me change this from 0 to, let's say maybe 1.5. Okay, and let me download that. And if I go into monitor mode here, and I pull up my custom monitor box that I just created, pull up here so you can see a little easier. So right now, my D20, which is my standard output for the instruction, and D22 is my deadband output, they're basically the same, right? Now, if you watch D1002, I'll increase it just a little bit, right? You can see it's in the 17,000s, now it's in the 18,000s, right? You'll see that D20, the output of the instruction, changed based on whatever D1002 is, right? You can see it's 27.56 roughly. The deadband output, however, didn't change. It's still at 26.7. So again, like we were talking about in the presentation, this can be used to kind of help filter out a little bit of small fluctuation in your input signal if you don't want that to affect your output. Now, as I continue to increase the 0 to 10 volt signal, you can see that my deadband will also start changing, right? Once it gets to about 1.5 difference, that's when the deadband output will update. Okay. And again, the only reason it's about 1.5 is because that's what I configured in that settings dialog box. Again, you've got access to those data registers in your program, so you can manipulate all those settings from within the logic of your code. Or if you've got this tied to a touchscreen, you can put numerical input fields on the touchscreen and let the operator adjust it. Okay. But I wanted to make sure I gave you an example of that scale instruction with deadband and without, just so you can see the difference to see how it works. All right. Now let's do the same thing, but we'll do it with an XYFS instruction. Okay. So if you guys remember, the XYFS instruction has to have an input. So what I'll do is I'll just use special internal relay M8120, since it only turns on once for one scan. I'll use that to initialize my XYFS instruction. Okay. My XY format set instruction is under advanced, coordinate conversion, and XYFS. Okay. Again, I could have just started typing in XY and then picked it from the pop-up list instead of going through the menu. Okay. And I'm going to hit enter just to make another run, just to move this up on the screen a little bit to make it easier to see. All right, so XY format set. We double click on this to edit it. Again, I'm going to scale 0 to 65,535, our 0 to 10 volt analog input. So what I want to do is change this data type from an integer to a word, 0 to 65,535. Source 1 can be any number between 0 and 29. Okay. If you guys remember from the presentation, we can do up to 30 XY format set instructions in a program. So we can choose any number here between 0 and 29. For example, if I use 15, okay. And again, you'll see where this comes into play here in just a moment. So now what I can do is go over here and start putting in my relationship between X and Y, right? And again, I can do up to 32 sets of XY points. So this is great if you've got something that's not linear. In our case, we only need 2 sets of points. It is linear. So when X is 0, 0 volts, I want to show 0 in the Y, 0%. Whenever X, my analog input, is 65,535, 10 volts, I want to show a Y value of 100. Okay. And again, if we had something that was nonlinear, we could have put in up to 32 different sets of points here. You can also see a graph of what your curve, in our case, it's a straight line, but if you click on this graph button, you can see what your curve is going to look like. In our case, we know since we have two sets of points, we know it's a straight line. Okay, that's all I need to do for XY format set. Now, what I will do is I will append, let me right click, I'll append a ladder line. So it just adds a ladder line below where I had my mouse at. And now I'll put in a convert X to Y instruction. I want to convert my X points, 0 to 65,535, into Y, 0 to 100%. And again, you can do that conversion whenever it makes sense for you and your program. For this example, I'm still going to use this 1 second clock. We'll do it once a second just so we can see it update. Okay. So I'll put in a normally open contact of M8121. I'll put in a 1-shot. And then I'll put in our convert X to Y instruction. Again, that's advanced data conversion. Coordinate conversion, sorry. Advanced coordinate conversion, and down to convert X to Y. I'll left click to drop that in, double click to edit it. Right. And now here, one thing we want to make sure we change is this data type, right? We're working with a word, 0 to 65,535. We want to make sure that the data type here matches that. So we'll change that to a word. Source 1, okay? Again, this is what ties this XY format set instruction to this conversion. So I'll put source 1 of 15 here. Again, remember, I could have up to 30 XYFS instructions, each with a different source 1 number from 0 to 29. So how I tell this conversion instruction what set of points, what conversion factor to use, is based off this source 1 number. When they match, when source 1 and the convert X to Y is the same as the source 1 and the XYFS instruction, that's what ties them together, okay? So my source 1 here is 15. My source 2 is going to be, what X values do I want to convert? Well, that's data register D1002, right? That's coming in from my analog input. I want to convert that 0 to 65,535 from my analog input. D1 is my destination. Simply, where do I want to store the converted value? Okay. So this will be my analog input scaled from 0 to 100. Okay. Let's download this. We'll take a look at it. Let me go into monitor mode. Okay. So, and actually, let me open up that scaling box again. And what I'm going to put in here, I'll add D30 as well. And D30 is coming from this convert X to Y instruction. It's a word. Okay. So what we should see, this is just two ways of doing the conversion. The scale instruction gives you a floating point output with the capability of doing deadband. The XY format set instruction allows you to do things that are nonlinear as well as linear, but it will give you a whole number output. There's no precision in this result, right? So what we'll see up here as I start changing D1002, which is my 0 to 10 volt analog sensor coming in, as I start changing that, we'll see D20, the output of the scale instruction, start changing. Again, we've still got that deadband setting in there, easy for me to say. So until the value in D20 is different than the value in D22 by about 1.5, we won't see that deadband output change. But what we should see is D30 change, right? The value in D30 should mimic what is in D20. It's just a whole number not a floating point. So let's look at it. All right, so if I start increasing my 0 to 10 volt input, you can see D1002 increasing. D20 and D30 are basically the same value, right? I'm showing 40.8 in D20, so it rounds up to 41. If I show 41 point, let me pull it back down a little bit, 41.1, again, I'm still showing 41. So it's going to round up or round down in D30, just depending upon where the signal's at. And still, you can see in D22 that because of the deadband setting, even though I'm at, about 42.2, 42.3, the value in D22, the deadband output is still at 41.6. So again, just a couple of different ways that you can use to convert and scale values. Let me go ahead and save that. And what I'll do now, that's really the end of the programming example. Let me take a look here at the chat and the questions, and I'll go through and answer all of them that I can. Again, we will send out a document that has all of the questions along with the answers in a PDF format that you guys can have as well. So let me see here. Here's some questions. It says, any reason not to use M8121 for S3 on your scale instruction? Excellent question. Oh, you meant, okay, somebody said no, I meant 8120. Okay, well, let me answer them both. If you use M8120 here for this initialization, what that means is once every second, or actually once every half second, because that 8121 is on for half a second, every half a second, it's going to push these values that you've got in the settings into these registers. So in other words, you really wouldn't be able to overwrite these registers for very long because M8121 would keep pushing these defaults back into the registers. Could you use M8120 here? Yeah, you could. What M8120 will do, again, that's your initialized pulse, your first scan bit. So whenever the PLC powers up on the first scan, it moves the default values into those registers. Yeah, you could absolutely do that. Good question. All right, let me take a look at the chat here and see if we've got any others. No, I don't see any others. All right, so we just had a couple of questions, that's fine. A couple of things that came up in the morning version of this webinar that may be beneficial for you guys. Let me cover just those couple of things. And then, obviously, well, you guys are certainly welcome to leave at any time. You don't have to stick around. But two things that were asked that can be handy in the morning session. One was, well, hey, you're doing, this scaling and conversion and stuff in the logic. Is there any reason that we could not have just done that in the card configuration, right? In the analog input card, when I go to configure that, I can change this binary data to an optional range, right? I had it going from 0 to 65,535. I could have came in here and said, you know what? I don't want that. I want that to go from 0 to 100. I could have scaled it right in here. Okay. This is perfectly legal. No reason that I could not have done this. Then what I would have seen was when I would have had 0 to 10 volts, that would have been scaled between 0 and 100 and stored in D1002. Okay. Perfectly legal. One thing to keep in mind though, if you do this, what you are in effect doing is you're changing the resolution of that card, right? Instead of using all 16 bits from 0 to 10 volts across 0 to 65,535, you're saying I'm changing it and using only a small portion of that, 0 to 100. So in effect, you're changing the resolution of the card. Now, is that a big deal? Depends on your application. If you're only looking for that kind of precision, or even if you wanted to do something like this, where I said, all right, Instead of 0 to 100, maybe I want to make it 0 to 1,000 so I can get 1 decimal point of precision. If that works for you, absolutely do it. That saves you time in the code, right? Now that will be, again, linearly converted. And if you need to put some filtering in, you can filter the setting here in the card setup. So that's perfectly legal to do, okay? Something else that was asked in the morning session was, what are these two checkboxes here in the analog module configuration? You'll see we've got use data register for setting parameters, okay, and FC4A compatible mode. What the use data register for setting parameters lets you do is, if you enable that, like right now, you'll see I'm only using 8 registers for this card, D1000 to D1007. If I turn that on, you'll see that jumps. Now I'm using D1008 through D1027. And what that is for is you can actually configure the signal type of the card, the data type, the min, the max. You can configure all this from within data registers in the PLC. So you can dynamically change these values. Even though you've got a program that's hard-coded, if you need to modify these settings, you can do it through the logic if you don't want to have to go back in and change them in this dialog box, okay? The FC4A compatible mode, what that lets you do is, when we designed the FC6A PLC, we wanted to make this thing the biggest, the baddest PLC that we've ever had, and we did. In order to do that, we also had to, unfortunately, redo the internal communications bus that the PLC uses to communicate with the I/O cards. The reason we had to do that is we wanted to be able to control more I/O and monitor more I/O. For example, the FC6A PLCs, you can do up to about a couple thousand digital and about 500 analog, okay? So in order to be able to process that, we needed to make sure that we could increase the speed at which the internal communication bus, we slap a card on there, how fast that thing could send data back to the PLC, right? It's no good if we've got a slow card, if we can do 2000 IO if the card's too slow. So unfortunately, we had to change that. What that means is any of the FC4A, FC5A series IO cards, they are not compatible with an FC6A PLC. In other words, I can't take an FC4A IO card and slap it on an FC6A PLC. It won't work, okay? But what we did do in the software is, because these cards have different data register mappings internally, how they're set up, we put this FC4A compatible mode in so you can choose the compatible card that you were using and have it mapped to those same registers. So you don't have to go and remap your analog IO cards, okay? So for example, if I turn this on, and right now I'm using an FC6A J4CN1 card, the FC4A equivalent is an FC4A J4CN1. You'll notice now my data registers here for my data and my status all got changed, right? We were using D1002 for our 0 to 10 volt input. Now it's D1047. Again, this is because I'm using FC4A compatible mode. So what this is really good for is, as you are migrating from FC4A, FC5A to an FC6A, you don't have to go through and remap all your analog IO points, okay? You don't have to worry about changing all those data registers in your code. You certainly can if you want to, but if you don't want to, you don't have to. You can just use that checkbox, okay? So just a couple of things that came up in the morning session that were good, that I thought were good. We've got some more questions that came in. Let's see what we've got here. Let's see. Why did you use M0 and just not use M8120 directly in the scale instruction? It's a good question. I could have done that. So here in the program, instead of having M8120 flip on M0 and then use M0 here, could I have just eliminated that and just done M8120 here? Yeah, absolutely. Would have done the same thing. Let's see. When you're downloading the program, what is the difference between downloading as binary and ASCII? Good question. So when you go to download, up at the top of the download dialog box, you've got two choices for transfer mode, binary or ASCII. And the truth is, and not to come off as flippant or as being a smart answer, it's really not. Anymore, it doesn't matter. You can choose either mode, it doesn't really matter. The reason this is in here is from back in the day when we had dial-up modems and we were doing remote access to a PLC that was tied to a dial-in modem. You had to match this to a setting within that modem. Again, anymore, it doesn't matter. But excellent question. Let's see, another question was, is the scan time less when you do the scaling on the analog card itself instead of the ladder? Yeah, it is, because I'm not using any logic within the program to do that. So, you know, like up here, where, well, down here really, where I'm scaling it. So, you know, this is taking up a little bit of scan time. It's not much. You know, again, I'm only doing this once every second. So it's really not putting much of a load on the scan of the PLC, but it is still taking up some of the scan. Yeah, for sure. Let's see, so if you're, another question was about the analog IO card. It says if you're doing that in the card itself, where I changed it, like in here from 0 to 100 instead of 0 to 65,535. It says you're doing that on that specific input and not on the card as a whole itself. Absolutely. So any scaling I do here, if I change this to 0 to 100, it's just on that input. Just on that input. Good question. Okay, let's see, we've got some more here. Question was, if you do that in the module, that wouldn't limit your use of the XY format set. That's right. So if you do the scaling within the module itself, that does free up more XY format sets that you can use, for sure. What is the reason to use an initialization on the scale instruction? That is, and I want to make sure I'm answering the question. There's an input to the scale instruction that it has to have just to function. Most of our instructions have to have some sort of an input to tell them when to work. There are instructions that we have that you can put up right against the left power rail. For example, like we have some data comparison instructions here that you can put up right against the left power rail without an input. So that'll work fine. The scale instruction, though, just unfortunately does need this input. Why we need this initialization bit here in the scale instruction, that is just so you tell it when you want those default values to be pushed into the working registers. It's just so you have control over it. That's all. Let's see, there's a question, will the FC4A cards slow down and the FC6A PLC? The cards themselves aren't compatible. You can't take an FC4A, FC5A card and plug it into an FC6A PLC. It won't work. In the module configuration here, if we do this, if we use this FC4A compatible mode setting, that really won't have any effect on the speed of the PLC either. So, you know, in other words, if you want to keep the mapping the same as what you had for your FC4A, FC5A PLCs, you can do this, no worries. It won't have any effect on the scan time. The only thing that it will do is it will use up more data registers, right? Just like in this example, here I'm using data register 1000 through data register 1057. I'm using 58 registers. Without that, even if I use data registers to set all the parameters, I'm only using 28 data registers. So that's really the only difference there. It's not, it won't have any effect on your scan time. It just has an effect on the number of data registers that you use. And, you know, we've got, what, 40, 48, 70,000, something like that. We've got a ton of data registers in this PLC. So it won't have an effect on your scan, just the number of registers that you use. All right, I don't have any other questions coming in. One other question that we did have in the morning session, it was about using tags. You know, when I was doing the ladder logic here, I just used the actual address for everything. I didn't use a tag. You can do tag programming with our PLCs, no problem. You can go into our tag editor and simply pick, for example, if I want to use my analog input, my 0 to 10 volt analog input, D1002, right? If I want to assign a tag to that, I can simply pick D1002. Let me scroll down here. D1002. I can come here and give it a tag name. You'll see the comment that I put in for the instruction listed in the tag editor as well here. You know, if I want to give this, you know, maybe this is my pressure sensor. Pressure sensor. Okay. What'll happen as soon as I give it that tag name, you'll see here in my scale instruction where I did have D1002 underneath source 1. You'll see now it shows my tag name, right? Pressure sensor. So I can go through and use my tag names throughout my program if I want to, instead of having to remember that was in D1002. Okay. You've also got the ability in the View tab, in the Show Hide section here of the ribbon, you can choose whether or not you want to show the actual device addresses or if you want to show your tag names, right? You can go back and forth. It's just a checkbox selection up here. Okay. We're getting some more questions. All right, let's see. We've got what causes D2 to change on the scale instruction? What's its purpose? Okay, so D2 here, these are 2 internal relays, and M20 will change whenever you're using the deadband setting. Well, it'll change if you're not using it, but when you're using deadband, when M20 will turn on is when, and yeah, I won't show it in here, but it'll show, that turns on. Let me go into monitor mode, I can show you. It only turns on for 1 scan, so we're probably not going to see it in monitor mode. We could put in some additional logic to catch it. So in other words, if M20 turns on, go to a single output and then set another internal relay so we can catch it turning on. But what M20 does is that turns on whenever the difference between D20 and D22 are regular output, which is not affected by deadband, and D22, which is our output that is affected by deadband. M20 will turn on for 1 scan whenever that difference is greater than our deadband setting. So in other words, in our example, whenever the difference between D20 and D22 is 1.5 or greater, M20 will turn on for 1 scan. M21, which is also part of D2, is an input value warning. That will turn on whenever my input value is either greater than the input maximum setting here, or less than my input minimum value setting. In our case, it's 0 to 65, 535. So the you know, the input value that we're getting in this case should never go outside of those bounds. Good question. Okay, what else do we have here? What other questions? As far as the analog, could you just recall in the configuration instead of using the FC4A checkbox? Let me see. I'm not. So instead of using this, could you just recall it in the configuration? I apologize. I'm not understanding what you're asking. Let me try to answer it. Again, I'm just not sure what you're asking. I apologize. You can turn on and off that FC4A compatible mode checkbox, and it will go back to whatever settings were before. But yes, I'm not sure what else you're asking. I apologize. Let's see, can you, oh, excellent. Yeah, can you save and import a tag name list? Is it editable in CSV? Yeah, absolutely. So for example, if I'm on my tag editor, I do not have to come in here and put in all my tags at all. What I would recommend doing is do one, come in, pick, whatever you want, data register, whatever, throw in a tag name, throw in a comment, and then export it. You can export it as a CSV or as a text file. Okay. I would do that just so you can see the format that our software wants the information in, what column is the address in, what column's the tag name, all that. Then you can go, and if you've already got tag lists developed, you don't have to go and reinvent the wheel and just redo everything, right? So you can just get your tag list together and then come and import it. Absolutely. Another question here, do you support user data structures? No, not yet, we don't. That is something that we are discussing. Any concerns with using M8125 as the initialization of the XYFS or the scale instructions? Yeah, absolutely. So on your XYFS instruction here, okay, you can do this pretty much whenever you want. The only exception to that rule is you do not want to do it every scan of the PLC. It'll screw up the conversion, okay? The reason being the PLC needs time to process what happened. If I turn it on at the end of the scan into the next scan, it needs to process what it was doing. If I'm continually turning it on and continually doing this XYFS, the convert instruction doesn't know exactly what to do, okay? So just don't use M8125 or anything that is always on to cause this XYFS instruction to always be on. Anything else you can use. On the scale instruction, no, you can scale that all the time. I don't think that has an issue. I have not tried that. I will do that though. I will try that and confirm that. I don't think it will be, but let me try that. I don't want to give you any wrong information. Okay, let's see. Let's see, there's another question here. If we're going to scale pressure from -10 PSI to 1,000 PSI using a 4 to 20 milliamp signal, if the negative PSI is less than 4 milliamps, how do you scale it? In the card configuration here, and let me pick another input. So if I'm scaling pressure here, and if you've got something that goes below 4, what I would do is I would use the 0 to 20 milliamp setting to catch that. But in either case, whatever you use here, 0 to 20 or 4 to 20 is what's going to be used to capture. So if you do use a 4 to 20 milliamp setting here, if you get something below 4, that's not going to affect your values here. It'll ignore it, okay? If you use 0 to 20, then anything above 0 milliamps will be affected in the scale here. Okay, good question. FC4A max is 50,000 on some of the cards, while FC6A is 65,535. Yes, that is absolutely true. The FC6A cards have just a touch more available resolution than some of the FC4A cards did. Very true. Another good question. Other than M8120 and M8121, what other addresses have unique pre-assigned characteristics? Excellent question. So in the software, we've got a bunch of what we call special internal relays and special data registers, okay? And those things have a predetermined function. It's basically what they do is already hard-coded in the firmware. You don't have to do anything to get them to work. A couple of ways that you can find out what those are. In the software, if you go in the tag editor, all of our what we call special registers or special internal relays start at the 8,000 level, okay? So in the tag editor, if I pull up my special internal relays, it'll show you here by address, and in the comment, it'll tell you kind of what they are, okay? You can do that for your special internal relays. You can do that for your special data registers. You can also, up in the top right-hand corner of the software, we've got a white question mark in a blue circle. If you click that drop down, you've also got a list here that'll bring up all your special internal relays and all of your special data registers. So for example, if I click on that, that'll open up the built-in help file and show you, since I chose special internal relays, it's going to show all those. And then once I get to the bottom, and there's a ton of them, it will explain in detail what each one of those things are. Okay, so you've always got that at your fingertips. You don't necessarily have to read the manual if you don't want to, although the manual is very good and very well written. But we made quick access to it here, so it's easy to find. Okay, let's see. You didn't show how to copy and paste instructions, contacts, coils, but I assume you can. Yeah, absolutely. So if I want to go in and let's say I want to copy that rung, I can either do, and like I said, I'm old, so I would still use DOS if they would let me. You can use Control-C, Control-V to copy and paste. You can also use, in the Home tab, we've got this clipboard for cut, copy, and paste. You can use these icons as well. So if I want to copy that rung and paste it again, I can do that. Or if I just want to do individual coils or what have you, you can absolutely do that. Cut, copy, and paste. My favorite instruction is the undo instruction, just because I make a lot of mistakes. That button is here on this quick access toolbar, this blue back arrow. You can also use Control and Z. So for example, if I hit Control Z, it's going to undo that paste where I just pasted that rung. Let's see, do you use one universal software to program your PLC, HMI, and so on? Within Automation Organizer, we've got a few different software packages. WindLadder, which is what I'm using now, is what we use to program all of our PLCs. WindOI NV is what we're going to use to program the HMIs. We do have some what we call all-in-one products, where it's an HMI and PLC all together in one product. That's our FT1A Touch series. That does have one software for it. That's WindOI NV3. It's included with Automation Organizer. You guys have that. But that does have the HMI and PLC software all rolled into one for that particular product. Good question. Okay, well, guys, that's I'm at the end of the questions. So if there aren't any more, I will go ahead and end the webinar. Just want to thank you all for taking the time out of your busy schedules to attend this. We appreciate it. We appreciate all the opportunities you guys give us to work with you. We are going to be doing these webinars for the next several weeks, especially while we're all, all confined or not as busy as we used to be a couple of days ago. These are going to be recorded, like I mentioned. Feel free to join in any of the ones that you want. I believe we've got these scheduled through about mid-April every day, with a couple of exceptions. I know we're not going to do one on Good Friday, and we're not doing any on Easter Monday, but we're doing them on a whole host of topics, and hopefully they are, beneficial for you guys. So, again, I'll end the webinar. You guys will be getting an email from our marketing department with a link for the software if you don't already have it, so you can get the software and actually have a full version of the software. You'll also get, a copy of this presentation, a copy of the program that's documented, with rung comments, and a copy of the questions with the answers to them as a document, so you can have that as well. A couple more questions popped in. Let me make sure, or are those just comments? I think these so far are just comments. So happy yesterday's technical difficulties got sorted out. Yes, we are too, very much. And glad you guys chose to join back up in this one. We ended up, as you guys know, we had to change platforms. We were using GoToMeeting. We had to go and change our package to GoToWebinar, which so far seems to have fixed the issues that we had. So, you know, unfortunately, we couldn't use the same links and same registrations and stuff that we'd already done. So we apologize for that, but we're happy we got this all figured out, and it seems to be working fine. We are also going to be redoing the Modbus webinars that we did yesterday. We know those from most people, we know those were just unusable, unlistenable, just due to the audio and video issues that we had. You know, we do apologize for that. But yes, we are going to reschedule those webinars. Modbus is something that, and I'm just throwing out a number, but I would estimate we use in probably 40% of the applications, if not more. So yeah, that's something we will absolutely be redoing and recording. All of these are going to be recorded and posted. So in any event, I will go ahead and end this if there's not any more questions. We appreciate everybody's time. Thank you guys so much, and we hope to see you again on another one soon.